Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone. I'm happy to introduce Benjamin Lee from Harvard University. Benjamin is one of Dave Brooks' students. He's finishing up his PhD in June. I think he's in the process of writing his thesis at this point. And he has worked on statistical inference and machine learning techniques for adapting microarchitectures and analyzing microarchitectures. And he'll be talking about his thesis work today.
All right. Thanks, Owner. Thanks for the invitation. And I'm very happy to be here. I was actually here a few weeks ago for ASPLOS, but I'm back. And I'm here to talk about my thesis work. And today I'll be making a case for statistical inference and its role in enabling efficient microarchitectural analysis. We'll show that there are new capabilities that we can get that weren't possible with the traditional approaches to microarchitectural analysis. Let's begin this discussion with a few broadly accepted technology trends. First of all, Moore's law has provided and will continue to provide increasing transistor densities. And this means for microarchitects that we have an increasingly abundant array of resources available to us to deliver performance. But on top of that, we also need to be able to deliver performance efficiently. And power is very much a design constraint. As important as it is to deliver performance, we need to ensure that we deliver it in a power efficient way. And both Moore's law and this emphasis on power efficiency has in part led to the transition to multi-core and parallelism. In the past, we had a uniprocessor. We recently have been seeing dual-core architectures coming into the market, and in the very near future, we will see quad-core architectures. But moving forward into the multi-core domain, we have a number of possible trajectories, and each of these trajectories are very different, but they're all possible for different domains or different market segments. You might observe homogeneous chip multiprocessors with a relatively small number of complex cores or a relatively large number of simple cores. You might also observe heterogeneous chip multiprocessors or systems on chip where we have a relatively small number of general purpose processing elements combined with a number of synergistic or special purpose processing elements. And because all of these design options are viable, we need to get a better understanding of what these cores will look like when we move into the future. This question of what the core should look like is complicated by what we observe in the industry. In particular, we're observing increasing design diversity. By this, we mean that there is increasing diversity in the set of interesting and viable designs being considered by our industry. And for examples, we can look at the IBM Power 6, the Intel Core 2, and the Sun UltraSpark T2. Each of these cores occupy very different parts of the design space. The Power 6 implements a relatively deep pipeline, whereas the Core 2 implements a relatively shallow pipeline. The UltraSpark T2 is also a perfect example of how designs that were considered infeasible for uniprocessor design have become feasible for multiprocessor design. Because the UltraSpark T2 is a very small in-order architecture, and as a result, they put a lot of these small cores onto a single chip to deliver thread-level parallelism. An example of the heterogeneous chip multiprocessor might be the IBM Cell Broadband Engine, where you have a power processing element on the same chip with a number of accelerators for vector operations. So this increasing design diversity means that we need efficient and rigorous analysis moving forward to assess the relative merits of these very different designs. On top of design diversity, we're also observing increasing metric diversity. This means that market segments are becoming increasingly differentiated, and as they become differentiated, they will have different priorities for various metrics. So for example, we might have single-threaded latency, aggregate throughput, power, and temperature as metrics of interest, but high-performance scientific computing, for example, might place a particular premium on latency, whereas commercial workloads might place a premium on throughput. And being able to balance these often conflicting design metrics will require efficient and rigorous optimization. The traditional approaches to dealing with and exploring design diversity and metric diversity is cycle-accurate simulation, at least for microarchitects. And architects will accurately identify the trends within the design space by tracking instructions as they progress through the microprocessor using some sort of simulator. And these simulators have proven very effective for estimating various metrics such as performance, power, or even temperature. The main problem with cycle-accurate simulation is its costs. First of all, we have costs per simulation, which are rather significant. To simulate a rather modest number of instructions, such as 100 million representative instructions, you might require somewhere between 30 to 90 minutes for a representative simulator, like the one we use. But cost per simulation is only part of the problem. The other part is the number of simulations required for design space exploration. The number of simulations will scale exponentially as we increase the number of parameters in our design space and the number of values each parameter can take. So we need a comprehensive approach that can deal with both parts of these costs. There's been quite a bit of work in controlling the cost per simulation, and we broadly classify these prior approaches into temporal sampling. Temporal sampling, the idea behind this is to sample representative instructions from the time domain. And behind most of these approaches is some sort of statistical profiling or some sort of basic block analysis that determines which instructions within the stream are most representative of the overall application. And in doing temporal sampling, we are able to reduce the costs per simulation because we're essentially reducing the size of the inputs to the simulators. However, we can see that this approach really doesn't do anything for us in terms of the number of simulations required. We still need to perform the same number of simulations to explore a design space. So we need to combine temporal sampling with spatial sampling. Spatial sampling will identify designs from the space, sample them, and run only those sample designs through cycle-accurate simulation. And this allows us to reduce the number of simulations essentially by performing the sampling. Once we have these samples, we need to assess broader trends within the space. And this is where statistical inference comes in. We need to construct inferential models from the samples and then use these samples as efficient surrogates for the underlying simulator. So, for example, we might construct empirically a closed form equation to represent performance as a function of various design parameters x, and we construct this closed form equation using these simulated designs as training data. And once we have this closed form equation, we can use this equation to perform our design space analysis instead of relying on further simulation. So this idea of spatial sampling combined with statistical inference leads us to a new simulation paradigm in which we comprehensively understand a design space by selectively simulating a modest number of designs from that space, and then more efficiently leverage that simulation data using techniques in statistical inference. If we talk about understanding a design space, we talk about specifying a large high-resolution space. A design space will be large in the sense that we consider a lot of different parameters simultaneously and thereby expose interactions between them within the design space. Given this large design space, we then sample points, in our case, uniformly at random, from the entire design space and run these samples through our cycle-accurate simulator. This sort of sampling allows us to decouple the high resolution of the space from the number of simulations needed to understand trends within the space. And lastly, we'll construct those inferential models to reveal trends and trade-offs and enable predictions for metrics of interest. In this case, we'll be talking about performance and power. So this leads us to the body of the talk. My talk will be divided broadly into three parts. First, I'll lay the foundation with statistical inference and show that we can construct efficient surrogates for microarchitectural simulators using a statistically rigorous framework. I'll then illustrate the new capabilities of this approach and show that we can now enable previously intractable analyses of energy efficiency for emerging design priorities, such as heterogeneous multiprocessors or adaptive architectures. And this will lay a very strong foundation for future research trajectories where I hope to pursue interdisciplinary research across the hardware-software interface and across the interface between engineering sciences and social sciences. But let's establish the foundation first with statistical inference. Statistical inference generally models relationships between data, and it does so by beginning with an initial data set to train or formulate the model. Once formulated, the model will leverage correlations from the initial data set to predict unobserved or unmeasured data points. We found that regression models are a particularly effective technique within this paradigm because for several reasons. First of all, they have low training costs. We showed that we can sample as few as 500 designs from a design space of 240 billion points and still construct effective models. In particular, these models were able to predict unmeasured or unsimulated points with median errors of 6% for both performance and power.
What would be the median difference? So what would be, so if you just picked two designs and randomly chose the difference between them? Or what would be the, I guess I want some comparison to a more naive approach. So if you just picked the average, how far off would you be? What would your median error be?
That is the median error. So we sample 100 points randomly from the space and look at the error distribution for those validation points.
Right, but I'm saying for 6%, 6% might be the average error if you just did one thing and then always guessed that for the other 240 billion. What I'm asking is, how do I know 6% is good compared to what you would just happen to get, you know, if you took your first one and picked the average and guessed that for the rest of the time?
So there are metrics to evaluate the difference between the difference between just simply using the average performance over the entire design space and the prediction we get from our model. Is that what you're asking? Maybe I can rephrase your question. Are you asking if how much better is our model than simply using the average from our training data?
Yeah.
Okay. So that typically is encapsulated by the R-squared statistic, and I don't have that number here, but it's typically for our model somewhere between 0.9 and 0.95. So in a sense, we're saying that the models are far more accurate than simply using the mean over the training data. So then the third point that regression models that I'd like to make about the regression models is their computational efficiency. Because evaluating regression models often boil down to matrix vector multiplies, we can very easily perform hundreds of predictions per second on modest computational resources, such as a laptop machine. So just to give you a quick background on regression, we assume that we have n simulated design samples, and we will use these simulated design samples to construct our regression models. And these samples are drawn from a design space with p different parameters. We measure the response from the simulator, and we denote that as y. And these responses could be either performance, power, or anything else that the simulator gives you. And we will predict the response as a function of various design parameters x, such as pipeline depth or various cache parameters. Regression will model each of these responses as a weighted sum of these p predictors, and the weights are typically known as coefficients and denoted as beta. And there will be some random error associated with these models. So, and these errors are typically assumed to be normally distributed with mean 0 and some constant variance. And there are a number of statistical analyses you can perform to actually make sure that this normality assumption holds. This is particularly important if you want to do significance testing further down the line. So I simplified the notation here, but we are actually dealing with piecewise cubic splines. So you might imagine performing some transformations on the x's before expressing the matrix vector multiply. So we do deal with nonlinear models, but just for the sake of explanation.
So piecewise cubic spline, how does that compare to other kernels? I mean, that's a kernel linear regression, right? Where you transform the variables into a new space, you do a linear regression model?
That's right.
Why did you choose that kernel over others?
Right. So we knew that simple linear regression would be insufficient. The other options we looked at were piecewise linear or piecewise quadratic models. And from the literature search that we did, the piecewise linear models are difficult to deal with because they have sharp intersections at the knots. And piecewise quadratic models are difficult to deal with just because the quadratic equations are difficult to handle. They're very large. They increase very quickly. So cubic polynomials tend to be more malleable. Please.
Is there anything special about this particular domain of microarchitectures that makes your model makes modeling different than modeling anything else?
Perhaps that will be clear in the next few slides, but we use our knowledge of the domain to specify interactions within the framework. So and that's actually on the next slide. We rely on what we already know about the microarchitectural design spaces to specify interactions. And this is useful in scenarios where you have two predictors, x1 and x2, that you shouldn't really separate. So the impact of x1 on y will depend on the value of x2 and vice versa. And then we can, if this is the case, we can construct a third predictor, x3, that is a product of the two. And we define these interactions using what we already know about the design space. So for example, if we know that x1 is the pipeline depth and x2 is the cache size, we know that the performance impact of pipelining will be affected by the number of memory stalls that you observe in the pipeline. So we specify this interaction based on this knowledge. And there are other sorts of interactions I'll go into a few slides later, but this is just an example of the sorts of interactions we can specify. Please. I'm sorry. So if x1 is pipeline depth and x2 is the cache size, then we should probably specify a product term within the functional model to try to capture those relationships, because you can't consider them separately. Because if you change the cache size, you're going to be changing the number of memory stalls per instruction within.
My question is simpler than that.
Okay.
I'm just asking, the formula on the bottom is not an x3 equals x1, x2, but are you saying that you're going to introduce a variable x3 of the form is a product of two other variables?
Yes.
Okay.
Yes. Right. But we found that we don't need to. The functional form of the relationship here does not necessarily need to match the transformation we do when we construct x3. At least that's what we found in practice. Right, because the example up there is a product, and here we're looking at.
So you're going to be doing the thing at the top? That's the kind of additional variable you're going to be introducing?
Yes. Yes. That's right. So the second consideration we need when we look at a regression within this framework is how we capture nonlinearities within the space. And as was mentioned earlier, we're going to observe nonlinearities based from diminishing marginal returns, for example, as you increase particular resource sizes, or if we actually observe hills and valleys within the design space. And we do this using restricted cubic splines. These splines will divide the predictor domain into intervals, and each of these intervals will be separated by a number of knots. And in this illustration, we have, this is just a simple cartoon in the sense that we have a parameter x. We divide the domain of x using 5 knots, and we fit separate coefficients to each of the sets of data within these intervals. So we essentially perform a cubic transformation on the x's before fitting the model. Once we fit the model and have determined the regression coefficients, we can evaluate the model for unobserved or unsimulated design points. And so suppose that we have a matrix X that defines a set of queries we want to make to the model. We can compute the expected response of the performance or power as a matrix vector multiply. And this follows from some simple statistics where we observe that the expectation of the errors was assumed to be 0, and the expectation of x beta is x beta itself, because both x and beta are known. So to construct these models, we're going to go through a derivation process that first performs correlation analyses to determine which microarchitectural parameters are most significant for predicting a metric of interest, such as performance or power. We perform this association and correlation analysis based on samples that we obtained from the design space. Once we have this significance testing completed, we can specify interactions and nonlinearities. We specify interactions based on our prior understanding of the domain, and we specify nonlinearities based on the significance test, as I'll mention later. Once we have the model, we can assess the fit of the model using standard metrics such as R squared. This metric compares simply using the mean from the training data versus using the model to predict your performance or power estimate. We can also then check the residuals for normality and randomness using various techniques to ensure that our model is not biased. And if we want, we can actually, this normality assumption becomes useful if we want to perform significance testing and try to prune terms from the regression model. The idea for model tuning is that you will take the terms in your model, you will perform significance testing and see how significantly it contributes to the accuracy of your model. And there are cases where you might be able to prune terms from your model, reduce the size of the model, and improve the efficiency of this approach. So as I mentioned earlier, we're going to define a design space and sample from it. We define a 15-parameter design space. This includes all of the standard superscalar out-of-order parameters within the microprocessor, including pipeline depth, superscalar width, various sizes of queues, tables, arrays, and various cache parameters, including size, associativity, and latencies. The second to last column specifies the range of values that we consider for each parameter. So if we're looking at superscalar width, we look at a width that ranges between 2, 4, and 8. And there are 3 different superscalar widths we consider within this design space. If we take the product of the numbers in this last column, we get the size of the design space. And this particular space contains 240 billion points. But the idea is that we can construct models for this very comprehensive design space. And in essence, if we can get the model, we can use that model as a surrogate for the standard microarchitectural simulator.
Why did you choose 115 as the highest latency for main memory?
So we started with a baseline in the middle of this range, and we just varied it. The idea is that if you, for example, included some L3 cache or something, that would reduce the effective, or that would impact the effective memory latency that the L2 cache would see, for example. So this is based around a baseline latency that we vary. So to collect our training samples, we use cycle-accurate simulators. These, in particular, we use Turandot, which is a simulator out of IBM. This simulator originally modeled the Power 4, Power 5 architecture, and we have since extended it to include a much larger design space that we showed on the previous slide. We supplement Turandot with Power Timer, which gives us power estimates from Power 4 circuit analyses. We use R, a software environment for statistical computing, to automate and script many of our correlation analyses, our statistical analyses, and our regression models. As I mentioned earlier, we sample 500 points from the design space I showed on the previous slide, and we select these points uniformly at random, as this gives us unbiased observations from the full range of parameter values. There are certainly more sophisticated techniques you could imagine to sample from the design space, but we find that uniform at random is sufficient for our work. When we specify the model, we will use domain knowledge to specify interactions between various parameters. So for example, we expect that superscalar width will interact with various structures that impact instruction bandwidth through the pipeline, such as the queues or the register file. We also expect depth to interact with the cache hierarchy, given the relationship between the memory stalls per instruction that you observe and the throughput gains that you get from pipelining. And lastly, we expect interactions between various levels of adjacent cache hierarchies, adjacent levels in the cache hierarchy, simply because of locality effects. We specified the degree of non-linearity using restricted cubic splines. If you recall, we had a figure where we could specify the number of knots we consider within a spline. And we will give weaker relationships fewer knots and stronger relationships additional knots. And the strength of a relationship will be determined by a correlation analysis. If we find that depth and the register file is more correlated with performance, we will give those parameters additional knots. And the idea is that these parameters are more important to fit accurately, and we give those particular parameters greater flexibility when we fit those models.
Are these the only interactions you specify, or?
These are the only interactions we specify. There are maybe a total of 6 or 7 for the design space.
Like, how did you choose these interactions?
So this is pretty much what we understand the interactions to be within a traditional microprocessor. So for example, if we look at the interactions between L1 and L2, if you have a very, or for example L2 and main memory latency, if you have a very long latency out to memory, then that will impact your optimal choice for your level 2 cache size.
But there could be some other interactions, for example, with the queues in the processor and memory latency
Right.
for your L2 size as well, right?
Right. So you could try to exhaustively look at all the possible interactions, and there are heuristics that allow you to do that. But essentially, we found that these sort of high order bits in terms of our understanding of where the interactions occur are sufficient. But you could certainly try and do a more exhaustive search. Please.
Did you model the branch predictor?
No, we didn't include the branch predictor in this space.
Was the processor out of order? Did it do speculative execution?
It is out of order, yes. Yes. So there's some dynamic instruction scheduling going on in the reorder buffer. Please.
Why
Right. So it seems like there are two schools of thought in terms of figuring out what interactions to include. One school of thought is that you can do significance testing and try to add and drop various interactions and try to assess which interaction is most significant. But we didn't go with that approach because we felt like that could potentially give us interactions that were inconsistent with what we already understood about the design space. Because the superscalar out of order design space tends to be relatively well understood intuitively, at least. So we decided to go with those. But you could certainly do, for example, stepwise regression and start adding and subtracting interactions and trying to assess the difference between the models.
Did you test that?
I did test it. And when I looked at the functional form of the model, I couldn't reconcile my prior understanding of the space with the sort of interactions that approach was giving me.
But did you have an error? Like, can you say that it has higher error than the model that you created using your domain knowledge?
So I found that it did have higher error, but it may not be a fair comparison because I spent far more effort in getting the model to work with these interactions than I did with trying to get the stepwise regression to give me what I wanted. So I'm not sure that it would be necessarily a fair comparison. I don't want to say that stepwise regression couldn't work, but it's something that. Any other?
One of the important interactions I would guess would be the size of the reorder buffer and your size of L2, because both of them determine how much latency you can tolerate.
That's true. So you can try to hide latency.
Not in the interaction space.
Right.
Because there are some previous studies that also looked at it. Probably you're aware of Brian Field's
Yeah.
interaction
Yeah.
space design work, and they found different interactions. They tried to exhaustively study
Mm-hmm.
the interactions between different structures,
Mm-hmm. Mm-hmm.
and they found more than the space you were looking at.
I see.
So I'm wondering what kind of error you're seeing because
Right. Well, because
it a priori eliminates some of the interactions.
Right. So if those interactions are indeed important and we don't fit it into the model, our model will not capture those interactions. The reason we ended up with this particular list is because those were the sort of interactions that would come to the top of anyone's mind at first blush. So you could certainly go and look at Brian Field's work in determining critical parameters and include those sort of interactions into the model, and that would probably increase the accuracy of the model. But the fact that we're seeing good accuracy given the small number of interactions means that we've effectively captured all the high order bits, I would think.
So, just to satisfy my curiosity, I assume when you start presenting results, you'll have some measure of the accuracy.
Yes, right. Yeah. Right. So we we quantify model accuracy by so we sampled points from the design space to construct the models, and then we sample another set of points to randomly from the design space to validate the model. And we collected 100 additional samples and looked at the error distributions using box plots. If you've never seen box plots before, the bottom of the box is the 25th percentile, the red line is median error, and the top of the box is the 75th percentile. And there is some statistical definition of what constitutes an outlier that I won't go into, but you can certainly ask me about it. But at a high level, what we observe here on the figure on the left is performance errors. So we're looking at simulator-reported performance numbers against regression-predicted performance numbers. And the figure on the right shows the power errors, the error distributions. The vertical axis...
Excuse me, the y-axis, every does percent?
Sorry, that should be relative error. Yes, percentage error.
Okay, so 0.1 is 10% error.
Yes. So the main takeaway from these figures is that the median errors tend to fall between 5 and 10% for a range of benchmarks we consider, and outliers tend to very rarely exceed 20%. And we imagine regression models being used in a context where you perform a very comprehensive high-level design analysis. And then once you figure out which region of the design space you're interested in, you're going to go and consider that particular region of the space with maybe further cycle-accurate simulation or more refined models specifically targeting that region of the space.
So I guess in terms of relative error, one of the things that will affect the relative error is going to be the total sort of variance in the space. Do you have a measure in that you can show, sort of if you just look across the entire space, how much variance there is between runs?
Right. So if you wait maybe 5 or 10 slides, you'll see that characterization. So at a high level, these sorts of errors make us sufficiently confident in these models so that we can apply them to early stage design optimizations, possibly combining it with more detailed cycle-accurate simulation further down the line once we figure out which areas we care about. So once we have these predictive models, we can apply them. And I mentioned at the beginning of the talk that we're going to be performing a number of new studies that were previously not possible. Some of these studies were looked at in the past, but they were looked at with cycle-accurate simulation. And as a result, they were highly constrained. And we're going to show that we can consider these same studies much more comprehensively than was previously possible. So to give you a quick idea of what we mean by qualitatively new capabilities, we have on the horizontal axis the number of parameters you might consider in a design space. And on the vertical axis, we have the size of the design space, assuming that each of these parameters contribute 5 different values to the space. So here we see that cycle-accurate simulation may be tractable for design spaces with a few hundred points or maybe a few thousand points. But once you go into the million or billion point regime, you will need to construct these inferential models, such as regression. Once you further increase the design space out to the billion or trillion point regime, you will need to combine the regression models with optimization heuristics that effectively traverse the space. If you're looking at small design spaces, you can exhaustively evaluate your regression models for every point in the space and try to get some understanding there. But for these larger spaces, you will need optimization heuristics, such as gradient ascent, genetic algorithms, things like that. So in this work, we originally proposed this approach in ASPLOS 2006 for 12 parameters and a billion point space. We subsequently reduced the size of the space to exhaustively evaluate our regression models and perform some studies for this slightly smaller space. We then increased the size of the design space and combined the models with an optimization heuristic, such as genetic algorithms in ASPLOS 2008. Here we considered a 240 billion point space and explored the potential from, for example, microarchitectural adaptivity. So the first sort of analysis that we're going to do is a Pareto analysis. And this is a sort of introductory analysis that any designer would do given a design space, just to understand the performance and power trade-offs. So just a bit of background, Pareto optimization improves at least one metric without negatively impacting any other metric. And in this work, the metrics we care about are performance and power. And the idea is that we want to identify the highest performance design for a given power budget or the most power efficient design for a given performance target. And we do this by first characterizing the design space and then simply reading off the Pareto frontier from this characterization. And we'll show that we have new capabilities with respect to comprehensive analysis. We can characterize and visualize the design space in a very comprehensive fashion. So if we take our design space of 375,000 points and plot them all into the power and delay space. Here we observe delay on inverse performance on the horizontal axis and power on the vertical axis. And this is essentially the spread that you were asking about earlier. We see for this particular workload, this is spec amp, that the 375,000 points span a wide range of delay values and power values. The color mapping for this figure corresponds to pipeline depth. So the blue points correspond to shallow pipelines, and the red points correspond to deep pipelines. And we consider 10 different pipeline depths, so that there are 10 different colors. And we can see that performance delay is reduced if we increase pipeline depth, but we incur significant power costs in doing so. And that's sort of an intuitive understanding that prior studies have exposed. We can change the color mapping to assess the parameter trends for other spaces, for other parameters as well. So if we change the color mapping, we see that there are 3 superscalar widths that we consider, and width will significantly impact performance and power.
Make sure my intuition is correct. So to me, that curve would be somewhere around the bottom left.
Right, somewhere around here. Yeah, so this is where you want to be. That's right. Right, so these are the trends for superscalar width. The register file is a particularly important parameter for spec amp. We see that if we increase the register file size, we will achieve significant reductions in delay. But we also see diminishing marginal returns here. The colors start stacking up as we move to the left, which means that after a certain point, the register file really isn't contributing much more to delay, and you've hit a wall in terms of how much you can achieve. Right. So the register file has a relatively small impact on power, especially relative to depth and width, for example. Right. The reservation stations has a really small impact compared to all the other parameters we considered. And the last parameter, level 2 cache, spec amp is not memory bound, especially compared to other spec workloads. And as a result, we see that we get very little in terms of delay reductions, but we incur a significant power cost by increasing the L2 cache as we move from the small caches in the red to the larger caches in the blue. So this is just a very quick way to comprehensively characterize the entire design space. And to give you a quick idea of the computational cost of this approach, once we've constructed our models using a few hundred sampled simulations, we can evaluate our regression models, and constructing this particular figure requires maybe 3.5 to 4 hours of prediction time on my laptop machine. And compare this to the traditional approach where this comprehensive characterization would be completely intractable. Given this characterization, we can simply read off the Pareto frontier by looking at the... What is the power model?
Yeah, how do you get the power numbers?
Right, so the power numbers are, as I mentioned earlier, we use power timer, and these power timer the power timer models are derived from power analyses of the power 4 circuits. So we get the unconstrained power, that is the CV squared F part of the power equation, from power 4 circuit implementations. And then we will scale that CV squared F component based on utilization that we measure from the performance model. So in this way, we can scale performance and power as we scale power as we increase, for example, the size of the register file by simply increasing the C component in your CV squared F equation.
Okay, so you do linear scaling.
So there has been prior work in showing that some of it might be superlinear, and we've accounted for example, the register file was found to be superlinear. So we've accounted for that. But in general, it's close to linear scaling.
And how do you choose what part of the application you look at?
These trace.
You validate your results?
I'm sorry?
Yeah, which part of the application do you look at?
So we use the same part of the application. We've obtained sampled traces from IBM, and although they don't use SimPoint, it's something very similar to SimPoint in the sense that they identify representative basic blocks and group them together. So we can read off the Pareto frontier, and we see here the blue triangles show the predicted Pareto frontier based on our regression models. And if we take each of these points and run them through our cycle-accurate simulator, we observe, again, broadly accurate trends. The red circles show the performance and power numbers that we get when we simulate each of those Pareto optima. And this is generally representative of the benchmark we considered. So Pareto analysis is a sort of introductory analysis that most people would consider when they are first given a design space, but we can imagine more sophisticated design characterization techniques. And in this second study, we're going to be talking about roughness analyses. In particular, if you have some performance and power topology, can we get a fundamental understanding of the roughness of it? How many hills and valleys are we going to find? How often are we going to hit plateaus? Things of that nature. And it's important to understand roughness because rough topologies are intuitively more interesting to the designer because there are simply more interesting design compromises to be made in rough topologies. But they're also more challenging to optimize. If you're running something like gradient ascent on a rough topology, you're more likely to get caught in some local optima. And knowing that a topology is rough may impact your implementation of your optimization heuristic. So the approach is to define and compute roughness metrics using our regression models, and then use those roughness metrics to identify interesting topologies, exposing them to the designer, and correlating roughness with optimization effectiveness so that we can implement heuristics that are robust in the face of optimization, or in the face of roughness. So the capabilities that we'll illustrate here are numerical derivatives and integrals to assess the roughness of the performance and power topology, and then using these roughness metrics to rank contours, providing interesting contours to the designer, and implement robust optimization to show that there are a number of strategies that you can use to mitigate roughness. So we compute roughness for a function f, and in this case, f is our regression model for performance, for power, or some combination of performance and power. And we derive, these roughness metrics were derived by Green and Silverman for spline-based regression models, which are exactly the sort of models we're using in this work. But the approach here is that we're going to take our roughness metrics, for example, R1 for a one-dimensional function f, R2 for a two-dimensional function f, and then this generalization Rd out to d dimensions. And we can take each of these metrics and compute these higher-order derivatives and these multidimensional integrals using difference approximations or Riemann sums. These are relatively simple approximations, and you could certainly imagine more sophisticated approximations. So once we have these roughness metrics, we can use them to rank contours based on their roughness. So for this work, we'll be looking at a particular benchmark, MCF, from the spec suite, and we'll be looking at the bips per watt metric. And if we want two-dimensional contour maps, there are p-choose-2 ways to generate these contour maps for a p-dimensional design space. And we're going to very quickly generate all of those p-choose-2 contour maps using our regression equations, and then rank them after we've computed our roughness metrics. And we'll show that the roughness metrics do indeed corroborate what we observe visually in the design space. So here we have two contour maps. These are contours that are ranked least rough of the 21, of the p-choose-2 contours. On the vertical axis, we have the bips per watt metric that we've standardized by subtracting off the mean and dividing by the standard deviation. And on the x and y axis, we have various pairs of design parameters. So here we see that these contours that are ranked least rough appear very smooth. The contour levels are very regular, and the planes are very flat. So in some sense, our roughness metrics are able to identify smooth contour maps and expose them to the designer. But perhaps more interestingly, we can also identify rougher contours. So these contours are in the middle of our contour rankings. And here we observe greater curvature in the contour levels, as well as greater curvature in the planes. The planes tend to curve up as we move into different parts of the space. And lastly, we can look at, sorry, go ahead.
Just a quick question. Has this roughness metric been, or similar metrics been used in other applications before?
So the only other known application, the only other application I know of is in statistical inference. And essentially, Green and Silverman, who first applied these roughness metrics, were applying it to figure out, to essentially penalize your model for roughness. Essentially, for example, if you want to say that, if you want a regression equation at the end that is least rough, you can incorporate it into your least squares approach. So you penalize least squares based on roughness. If you want a rougher model, you can reduce the penalty and so on. So that's the original application of these roughness metrics. But we're applying it to determine which contours are most interesting. And just to end this discussion, the contours with the highest roughness are shown here. These contours are clearly rougher than any of the contours on the previous slides. We have a saddle point in the figure on the left and a saddle point in the figure on the right. So the idea is that we can take our roughness metrics and validate it for these two-dimensional contours. And because what we observe visually confirms what we quantify with our metrics, we can have confidence in applying these metrics to higher dimensions, such as the seven-dimensional, full seven-dimensional space. Furthermore, this analysis gives us a way to expose and rank interesting contour maps to the designer. Because these contour maps are so very easy to construct now with our regression equations, you can very easily generate hundreds of these contour maps. But these roughness metrics essentially remove a lot of the subjectivity involved in looking at these maps. You're no longer trying to eyeball two contours and trying to figure out which is more important. We can use these metrics and rank them and give the designer some guidance there. I also mentioned that roughness impacts optimization effectiveness. And here we see that a relationship between the roughness of the 7-dimensional space and the deficiency of an optimization heuristic, in this case, gradient ascent. We have our noun workloads here, and we consider first the ranking by roughness. For example, MCF is one of the least rough topologies, and gzip is one of the most rough topologies. And we also compare it against the rankings for gradient ascent. So if we know exactly the true global optimum within the space, and we know the results being reported by gradient ascent, we can compare the two and compute the deficiency. That is the difference between the heuristic and the true value. We can then compare the two and find that there is some relationship between roughness and deficiency. Smooth topologies tend to have lower deficiency, and rough topologies tend to have rougher deficiency, have higher deficiencies. And overall, we observe a correlation of 0.35 between the two. Right, so those are ranks. Yes, yes.
Yeah, so, sorry. So, were they evenly spaced, or for something like this? Did you wind up, if you had looked at the absolute roughness as opposed to simply ordering them, did you? The problem with numbers like this is I have no idea if it's as far from 1 to 2 as it is from 2 to 9.
I see.
So, were they evenly spaced?
I would say that they're not evenly spaced. I remember looking at the absolute values, but I don't remember. But they were not evenly spaced. So your point is well taken. Okay, sorry. Right. But the idea is that there may be some contribution of roughness to the deficiency of your heuristic, and we can try to mitigate that roughness using either additional trials in your implementation of gradient ascent, or using some stochastic version of the heuristic that allows you to go down hills occasionally.
Remember the bottom right is the correlation coefficients between the ordinals. Is that what that means?
Yes. So yeah, that's right. Right. So those first two studies were primarily characterization-based studies in the sense that we weren't looking at design analysis necessarily, but we were trying to get a better understanding of the design space. I'll present two more studies on actual design paradigms that are of interest to the community today. The first of which is multiprocessor heterogeneity. The question here is, if we have a multi-core architecture and we want to identify the best core designs, how much can we get by implementing different core designs that adapt to different parts of your application suite? And the idea is that heterogeneous core design allows you to mitigate the performance and power penalties associated with the cost of just a homogeneous single design compromise. So the approach here is to construct our models and use them to identify the most effective architecture for each workload we consider. And then we identify design compromises among these optima using a clustering analysis. And we'll be showing here capabilities in assessing efficiency trends and limits from heterogeneity and showing that that regression models can play nicely with exhaustive optimization and clustering techniques. So first, efficiency trends and limits. So this figure shows the number of clusters we consider when we do our k-means clustering. Cluster count 0 is simply a power 4-like baseline. Cluster count 1 refers to a homogeneous CMP, where we identify a single design compromise that's best for the average of the workloads. And as we move to the right, we increase the degree of heterogeneity such that when we hit a cluster count of 9, each workload has its own core design on the CMP. And this sort of analysis has been tried in the past, but it's very difficult to implement using simulation. But we can make a number of high-level conclusions. First of all, if you simply use a homogeneous CMP, you may be increasing the performance of some workloads at the expense of others. One thing to note would be that the MCF workload here has a 60% reduction, or sorry, 40% reduction in efficiency, while MESA has a 4.6x increase in efficiency. if we increase the cluster count out to 4, that is, we implement 4 different core designs on our CMP, we see that the average efficiency jumps to 2.4x, and all of the benchmarks get to benefit from this customization. It's also useful to note that there's a very clear need in this figure at a cluster count of 4, because with 4 cores, we get a 2.1x increase in efficiency, whereas if we were to go to the extreme case, we would only get a 2.5x. So the difference there is not very significant, and this tells us that for this particular set of workloads, we want 4 different cores on our CMP.
Did you do the same study with just performance as opposed to this power performance product?
No, we didn't.
Okay, why? Just curious.
That's just the flavor of our research. All of our analyses incorporate power in some way. I guess we've never thought about looking at just performance. Please.
So is the analysis that you're doing on the 4 cluster point imagining a chip that has 4 cores where only 1 is active for every one of these workloads?
That is true, although you can imagine. So the idea is that when you run any application, will there be a core that is best? What is the efficiency gains that you can get if there is a core that is most suited for your application? It does not imagine scenarios where 2 similar applications are contending for the same core.
If you had considered just the performance and not the performance efficiency relative to power, the average should be increasing monotonically, yes, or at least non-decreasing monotonically. You've got a decrease from 4 to 5, and presumably that's because you're burning more power now that you've got, you're burning more real estate and therefore burning more power.
Right.
Is that not the case? It would be monotonically not decreasing, yes?
Yes, because if you, for example, MCF is somewhat unique of these 9 benchmarks in the sense that it requires a large cache. So if you're looking at some of these smaller cluster counts, MCF, it really isn't being satisfied, and there is no large cache. There's no core with a large cache. So once you give MCF the core that it wants, the power cost will significantly go up. That's right.
John's question is between 4 and 5, it looks like your metric goes down.
Right.
And at first blush, you would think, well, you build a 5-core thing where the 5th core was empty, right? And you could pay for it.
Sure. Right. So you could implement the core and turn it off. Sure.
So I guess part of the question could be answered by what else is going on in the chip other than the cores? Like how do you structure the other shared resources? Like what are your assumptions?
Right. So the thing is, we are not using a multi-core simulator to evaluate these options. These are essentially considering the cores in isolation of each other, and they're not contending for shared resources.
Okay. So you're assuming a fixed cache size, for example?
Right. So a fixed cache size that would vary from core to core, for example. Well, once you've determined the most efficient designs for your 4 cores, for example, your cache sizes would be fixed for those 4 designs.
So your cache size is part of the optimization?
Yes.
How about the memory?
It's not included in.
So you're assuming they have separate memory hierarchies?
So the earliest point of contention. So first of all, we don't model contention, but in this sort of analysis, the earliest point of contention would probably be a DRAM or memory.
Is there some intuition why certain applications, say Mesa, for instance, is like fluctuating a lot? So if you go from 1 to 2, it's going down a lot, and then 3 is the same, and then 4 it goes up, and then 5 goes down again.
Well, when you perform k-means clustering and you add additional centroids, essentially, that could potentially change the compromises found in your previous in your previous clusters. So in a sense, we looked at this particular knee and we did not find any intuitive reason for why this knee would occur. So we suspect that it's a clustering anomaly.
That's right, but I mean the MESA application is
Sure.
very striking, right? There must be something that's just that's kind of right in the middle between two clusters or something, and
Right.
if you switch it this way or that way,
Right.
it has a huge impact on that
Right.
specific application. So, do you know what that could be, or you know,
So maybe the next slide will show you, but I didn't. We didn't see that Mesa was particularly close to any other cluster. So yeah. So given that given that we observed the knee in the trends and we saw that 4 cores was a good number of heterogeneous cores, then the question becomes, what should these cores look like? And for this, we look at the actual results of the clustering analysis. And here we observe 4 clusters. The circles represent the compromise architectures, and the points radiating out from the circles correspond to the per benchmark optima that we used to construct that compromise. So for example, the cluster 1 up at the top, that particular compromise was constructed from the optimal architectures for JBB and Mesa. At a high level, we can make a number of conclusions from this figure. First of all, we observe that the performance and power penalties associated with these compromises tends to be rather small. The centroid is often very close to the per benchmark optima, and as a result, we have succeeded in mitigating the performance and power penalties. The second thing we can observe from this figure is that this could be potentially an approach to assessing similarity between workloads based on their microarchitectural resource requirements. You could, for example, make some claim that JBB and Mesa are very similar workloads, given that they require similar resources at the microarchitectural level. And lastly, the third point I'd like to make about this figure is that we essentially can span very different parts of the space with this clustering analysis. If we look at depth and width, for example, we see that cluster 1 implements a deep, wide pipeline. Cluster 2 implements a shallow, wide pipeline. Cluster 3 implements a deep, narrow pipeline. And cluster 4 implements a shallow, narrow pipeline. So those are all the 4 combinations we considered for pipeline depth and superscalar width. And essentially, we captured the 4 corners of the design space. And the idea here is that this coincides very well with our objective that I began with at the beginning of this talk, which is to deal with design diversity and make these relative assessments between very different parts of the design space. So the fourth and final study that I'll be talking about is a study of microarchitectural adaptivity. The idea behind adaptive microarchitectures is that we can allocate hardware resources at runtime to match application dynamics. And we want to do this to enhance performance while localizing the power costs. The idea is that if a particular part of the application requires a particular number of resources, then the hardware can provide those resources, but power those resources down when they're not in use. So we can localize the power cost, but essentially over-provision the hardware. Our approach is to consider both high temporal and high spatial adaptivity. High temporal adaptivity refers to the frequency at which you reconfigure your hardware. And high spatial adaptivity refers to the number of parameters or number of designs that your hardware can adapt to. And this sort of dimensionality is very challenging because if you consider both, you will have a lot of small intervals, and for each of these intervals, you need to adapt and identify the best design over a very large space. So for this analysis, we'll first quantify the potential bits cubed per watt efficiencies that we get from hardware adaptivity. And we then can identify significant adaptive parameters. Which of these 15 parameters that we consider are most significant when it comes to adapting the hardware? Can we get away with not adapting some of them, for example? And we'll show, again, capabilities in efficiency trends and limits, and we'll show an integrated framework that combines analysis with heuristic optimization, in particular genetic algorithms. So we begin this framework, again, with temporal sampling, which we saw at the beginning of the talk. We then, given a series of representative instructions, we'll break those instructions into a number of adaptive intervals. In this work, we consider more than 1,000 of these small intervals, each with 80,000 instructions. Once we have these adaptive intervals, we will in parallel define our adaptive design space in very much the same way we defined our design space earlier in the talk. We can collect samples from this design space and run each of these adaptive intervals through psychoaccurate simulation to get one regression model for each of those m adaptive intervals. Once we have these regression models, we can use it to implement a robust version of genetic algorithms. And the genetic algorithms will effectively search that space of 240 billion points and identify the best architecture for each of these small intervals. And this will allow us to assess the potential efficiencies that we can get from microarchitectural adaptivity, essentially a limit study. So this figure illustrates the performance and power impact of this high degree of temporal and spatial adaptivity. We have very short instruction intervals with 80,000 instructions each. And we adapt over a space of 240 billion points. The figure on the left shows the performance and power impact. So we can see that virtually all of the workloads have some combination of performance increases combined with power reductions, as shown in the blue bars and in the red bars. These trends in performance and power will translate into efficiency gains. And with the exception of MESA, which doesn't utilize the adaptivity we give it, probably because there's very little dynamic application behavior, we can see that the efficiency increases range from 1.6x for radiosity out to 5.3x for GCC. So these are rather significant gains, and given this sort of rigorous benefit analysis, the question then becomes, what are the costs of this analysis? And this sort of study is essentially to motivate further research in terms of hardware costs as well as circuit costs in terms of implementing this, and also software costs in terms of control algorithms needed to accurately figure out which of these designs are most effective for each interval.
In the previous adaptivity figure, what is the overhead of adapting?
Right.
So, get these performance numbers or power numbers?
Right. So in the sense that we do not consider those overheads, this is a limit study.
Okay, so basically at the end of an 80K instruction interval, you assume that you can switch to
Right, switch instantaneously to the next design. Because those overheads are very specific to the implementation of the adaptivity and specific to the control algorithm.
So when you get the numbers, basically how do you get the numbers? The performance numbers.
How do I get the performance numbers?
Yeah.
So we look at the performance of each adaptive of each interval.
Okay.
Right.
So you basically add them up.
Right.
Maybe I'm once again anticipating the next slide, but how sensitive are you to how many instructions per interval there are?
I'm sorry, but I didn't include those slides. But our original paper had that trend, and what we did was 80,000 instructions was the finest degree of temporal adaptivity, and we progressively doubled that size and looked at the trends that we observed. So as you might expect, increasing the frequency will monotonically improve efficiency.
I just wanted to get a sense of if the overhead turns out to be this, then where do you fall off? How many instructions per interval? At what point is it not really worth it? Do you not get a lot of benefit from it?
I see. Yeah, I don't have those numbers off the top of my head. I can get back to you on that. Okay. So the next question might be, how many of these 15 parameters are actually significant for adaptivity? And the answer is, more often than not, you can get a very large fraction of your total potential by using a very small number of parameters. We found that on average, you can get 60% of your potential with only one parameter, 71% of your potential with two parameters, and 77% of your potential with three parameters. So for example, APPLU achieves a very large fraction of its potential with three parameters. The main catch here is that these three parameters will differ across workload to workload. So the three parameters that are most significant for APPLU and actually delivers this high fraction of potential will be different from the three parameters necessary for radiosity to deliver this high fraction of potential. And this is a problem from the hardware perspective, because this means you don't know a priori which application you're going to be running, and you don't know a priori which parameters need to be adapted. So if you could somehow implement that adaptivity, the capability to adapt for all of your 15 parameters, and then at runtime trying to shrink that down, you still incur the hardware cost, but because you're only adapting 3 parameters, you have significantly smaller software control costs because you don't need to predict the performance as a function of 15 parameters. You only have to predict performance as a function of the 3 that you're actually adapting for a given workload. So to just summarize this part of the talk, I've presented 4 applications of our regression models. On one side, we have some fundamental analyses of design characterization. We began with a rather simple analysis of Pareto Frontiers, and we went on to a more sophisticated analysis of roughness and computing roughness using numerical derivatives and integrals. On the other side, we have a number of fundamental design studies for two design paradigms that are of interest to the hardware community. Multiprocessor heterogeneity and microarchitectural adaptivity. And in both cases, we showed that we could quantify efficiency trends and limits by combining regression models with other techniques such as clustering or heuristic optimization like genetic algorithms. So that's the end of the second part of the talk. I'd just like to quickly end by talking about some potential for future work and in general areas in the future I'm interested in. In particular, I'm interested in interdisciplinary research across the hardware-software interface and potentially across various domains spanning technology, policy, and economics. So if we look first at the hardware-software interface, there's a lot of potential to apply this approach up and down the hardware-software stack. At the application level, I've had some experience in applying this methodology for performance tuning of parallel applications. How do you search a design space? How do you search the parameter tuning design space when it comes to applications and, for example, doing data decomposition on a parallel workload? And for the compilers, at the compiler level, there's been a lot of work in machine learning for compiler optimization flags, essentially trying to predict the performance impact of various combinations of flags. But a lot of these analyses treat optimization as a black box. And really, the designer or the user doesn't really know the interactions between these various optimization flags. So in what sense can what role can our statistical inference play in exposing some of these interactions in a robust way instead of just treating it as a black box? There's still quite a bit of work that could be done at the architectural level, especially as we consider multiprocessor and systems on chip. We will need to account for the interaction between these cores. Much of the work I've looked at has been focused on the core design itself. But how do we actually consider the interaction between these cores and account for that in our performance and power models? And lastly, we can go below the hardware-software interface and look at device modeling, especially its role in process variations and how process variations will impact the performance of future systems when we go to the nanoscale fabrication. So I'd just like to quickly comment on some preliminary work that I've done in 2 of these areas on both sides of the interface, the application interface and the circuits, or the application side and the circuit side. So in the application side, I've shown that we can predict the performance of parallel programs as a function of data decomposition, process topology, and algorithmic implementation. In particular, I looked at 2 workloads, semi-coarsening multigrid and high-performance LIMPAC. These are fairly standard kernels in scientific computing. Multigrid solves discretized 3-dimensional differential equations, and LIMPAC solves dense linear systems by doing an LU decomposition followed by backward substitution. Both of these cases give you a large chunk of data and decompose this data across a number of processes. But the question then becomes, how should you decompose this data across, and how should you distribute the processes across this work? And we showed that we could predict performance as a function of these parameters with 10% median error with respect to real system measurements on a 512-node blue gene at Lawrence Livermore National Laboratory. And this sort of parallel performance tuning will become more important in the future as designers or programmers will specify at a very high level parallelism and rely on these heuristics to extract more detailed performance numbers out of the machine. On the other side of the interface, I've also worked with device models. Here we predict DRAM retention time as a function of threshold voltages. And we looked at a novel DRAM cell architecture, which is known as 3T1D. It contains 3 access transistors and a diode that stores the charge. And we showed that we can predict this retention time with median error of 7% with respect to detailed circuit simulations. And this sort of analysis is particularly important if we suspect that each of these nodes or each of these devices undergo some sort of process variation as we go to more advanced process technologies. So what impact will these process variations have on the overall retention time of the memory? Our regression models can play a role in answering that question. And to conclude, lastly, on some tangentially related work that I've done, I'm interested broadly in the environmental sustainability of digital infrastructure. There's certainly been quite a bit of work in understanding the fundamental technology behind this. There's been a trend towards centralization of compute resources with data centers providing web service and application service. And there's been a lot of understanding about the hardware, the system, and the facility implications of the centralization. But there's been less work in terms of understanding the policy and economic implications of these approaches. So for example, if you look at statistics showing that India has very effectively developed its IT infrastructure, but yet 50% of its people still live without electricity, the question then becomes, is their infrastructure development equitable in the sense that are they over-provisioning electricity to technology hubs while leaving other parts of the country without power? And in other work, I've also shown that if you want to understand the environmental impact of digital infrastructure, you need to look at substitution effects. And essentially, to what degree do digital practices substitute traditional practices? And for example, you might be downloading a lot of PDFs and thinking that you're going to save some trees because you're not going out and buying books, for example. But more often than not, you're going to be going out and printing out that PDF to read it anyway. So the question is, you're burning the electricity involved in delivering that PDF to you, and you're also burning having more traditional environmental impact. So all of these approaches will need some market-driven approach where industry and organizations will compete based on corporate social responsibility and make sure that they essentially compete based on their digital sustainability. This concludes my talk. My talk, again, had 3 parts. I first talked about statistical inference and the fundamentally new capabilities inference provides us as architects. And I've also suggested that these fundamental capabilities can extend across the hardware-software interface and possibly across the divide between engineering sciences and social sciences. At this point, I'd be happy to take any other questions you might have. Thank you very much.
Any other questions?
All right, thank you.